Here's problem 22. 10 kilograms of water at 0 degrees Celsius is mixed with 10 kilograms of water at 100 degrees Celsius. The change in entropy in calories per Kelvin of the system is, well, in general, if we're going to change a substance like this, every little infinitesimal change or heat added is going to cause a change in temperature according to MC delta T. If we were to integrate this so that we would get our change in entropy is equal to initial to final, our change in Q over a reversible process over T. So this is equal to MC integration from initial to final dt over T, which will be MC natural log of T from initial to final, which would be natural log of T final, if I can get this right, over T initial. So that is what we're going to be looking for. So in this case, we want to find what the final temperature is of this mixture of water. All right, that's another question. We're going to say that the heat added to water number 1 in order to warm it up, plus the heat lost from water number 2 in order to cool it down, will be equal to 0. In other words, within the system, there's not going to be any heat added total from the external environment. So we'll have M1, specific heat of water, delta T1, plus mass 2, specific heat of water, delta T2, should equal 0. We have 10 kilograms, so 10,000 grams. Specific heat of water is 1 calorie per gram per degree Celsius. We had some kind of final temperature minus our initial temperature of 0 for the first 10 kilograms of water, plus 10 kilograms, specific heat of 1, times final temperature of T minus our initial temperature of 100 for the second 10 kilograms. Let's divide both sides by 10,000. Get rid of that. And we're going to end up with something that looks like this. 2T minus 100 equals 0, or T is going to equal 100 divided by 2, 50 degrees Celsius. Nice to know. I've always wanted to know that, but we want to calculate the change in entropy, so we want to calculate this. Well, let's calculate the change in entropy for the first bit of water. That's going to be equal to mass 1, specific heat of water, natural log, T final over T initial. Now in this case, our T final is 50 degrees Celsius, but if we're going to use it in this equation, we're going to have to change it to Kelvin. So that's going to be 50 plus 273.15, 323.15. And of course our initial is 0 degrees Celsius, or 273.15. So this is going to be equal to 10,000 times 1 times natural log 323.15 over 273.15. What does that give us? 323.15 divided by 273.15 natural log times 10,000 is 1680.9, and that will be joules per Kelvin. Actually, calories per Kelvin, sorry. Everything was done in calories. That's going to be calories per Kelvin. All right, for our delta S2, that's going to be mass 2, specific heat of water, natural log of our T final over our T initial. For this one, T final is again 323.15 Kelvin Wish I had put the K up here. And our initial is 100 degrees Celsius, so that's going to be 373.15 Kelvin. So that will make this 10,000 times specific heat of water, 1 calorie per gram per degree Kelvin, natural log 323.15 over 373.15. And what is that? 323.15 373.15 natural log times 10. Has a negative 1438.6 calories per Kelvin. Our total change in entropy for this process of mixing will be the sum of these two entropies. So that's going to be equal to 1680.9 plus a negative 1438.6. Giving us a total of 242.3 calories per Kelvin. Positive entropy for the whole process of mixing. So our change in entropy for this problem is 242.3 calories per Kelvin.